Hello. So in this video, we're going to talk about Haberman's section 4.4, where the goal is to solve the wave equation with boundary condition, right, such that the ends of the string are kind of tied down. Okay. And in the process, we'll talk about a few other, you might say, more like physical notions or introduce some vocabulary that shows up a lot with these sorts of things. But kind of when we get down to it, the goal is just to solve the wave equation and construct solutions to that. Okay, so recall, right, so what is the wave equation? Well, this is the wave equation right here. Okay. And so kind of what are the pieces involved? Well, the picture is the following. So right, this would be our x-axis. And thinking is that if you have a string that's not moving, right, so it's at rest or equilibrium, so the string is sitting right here. And so what is this function u that we're looking for? Well, this function u, go like this. Right, what we're looking for here is a function that describes the displacement of the string kind of throughout time. Okay. So this is the evolution of the displacement. Okay. These are the boundary conditions. And so the interpretation here is, right, the string is tied down, so the displacement of the string at the point x equals 0 is 0 for all time. Likewise, the displacement at L is 0 for all time. Okay, so these tell you that the string is tied down at the ends. So those give us boundary conditions. The other piece we need are initial conditions, right? Because we have two time derivatives, we're going to need two initial conditions in time, right? Two pieces of information in time to kind of tell us how right, this process starts. And so for us, those two pieces of time information are going to be the profile of the string, the displacement of the string at time 0. And so that profile is going to be some function f of x. But we also need a second piece of information for time. And so what we're going to do is describe the initial velocity of the string at time 0. And so all of this information is enough to kind of uniquely determine the solution to this problem. Yeah. Okay. So how are we actually going to solve this PDE? Well, in this case, we're going to use the same technique we've been using already. And that's the technique of separation of variables. Okay, so here we're going to seek a solution of this form, right, where we've split up right, our solution into a piece that just depends on space times a piece that just depends on time. Plug this into the ODE, or sorry, PDE, where recall the PDE is d squared u dt squared is equal to c squared d squared u dx squared. Okay, so plug this into here. You're going to end up with this expression where you've already moved things around. Okay, and so here I want to point out that it's a lot more convenient to keep the c squared attached to h and the time pieces as opposed to the spatial pieces. Okay, but otherwise, right, move things around. You get this, right? This side just depends on t. This side just depends on x. So they're both equal to some constant. We're going to call that constant minus lambda. And so then we're left with this system of ODEs. Okay. Okay, well, what's next? Well, we have boundary conditions, right? So going back here, right, we have these boundary conditions. So now what we want to do is see what these boundary conditions are in terms of kind of our separated solution. And so the boundary conditions in terms of our separated solution look like this. Okay. So here, right, what we're working with now is these boundary conditions plus the fact that d squared phi dx squared is equal to minus lambda phi, all of this information, right? This is one of the kind of black box eigenvalue problems that we've already solved. This implies that, let me write it like this. This implies that lambda is equal to n pi over L squared, and phi of x is equal to sine of n pi over L x, which is exactly what's written here. Okay, right, but this is one of the black box ODEs or eigenvalue problems that we've already solved. We've worked with plenty of time, so in this case, we'll jump to the final form of the solution. Okay. Okay. So that's figuring out what the spatial piece is, right? We also need to figure out what the time piece is. Okay, so if we go back and look at what the ODE for H is, we get this expression. Okay. And so here, keep in mind that this is not an eigenvalue problem, right? Because here, we're not trying to determine what lambda is. We already know what lambda is, right? So this expression, if we plug in what lambda is, this is going to give us minus n pi over L squared, c squared, h. Okay. And so now this is a constant coefficient, second order ODE, where we have a minus quantity or constant times h. But the thing is, right, this piece right here is positive. Okay. And so all of this gives solutions this. Okay. I mean, you can double check, right? So like, for example, if you start with the solution, take the derivative, you're going to get C1 times C n pi over L minus C1 that, cosine n pi over L C n pi over LT plus C2 times C n pi over L cosine, wait, no, first one should be sine. Cosine of C n pi over LT. Okay. Take another derivative. H double prime of t is going to be minus C1 C squared n pi over L squared cosine n pi over LT, C in front, minus C2 and C squared n pi over L squared sine C n pi over L T. And then this expression right here is exactly right minus C squared n pi over L squared H as desired. Right. So yeah, however you want to go about it, right? The point is that this expression right here solves this. And it's the most general expression we can use. And so this right here is the corresponding time piece for the separation of variables problem. Okay. So now what we do, right, as we usually do, let's plug in the building blocks, this times this, and use the principle of superposition to kind of write the most general solution we can to this problem. And so our general solution here is going to be a linear combination of all of these kind of basic building blocks that we computed. Okay. And so if we actually compute what this product is, right, well, phi sub n is just this single term. So distribute this piece there and there. rename C1 to A sub n and C2 to B sub n. And then otherwise, yeah, our solution U of x comma t is equal to this. Okay, so this is kind of the most general solution we can construct to the wave, kind of the problem that we posed at the start using the wave equation. Okay, but yeah, this is our most general solution. Okay, so now of course the question is, well, how do we get these coefficients A sub n and B sub n? Okay. Notice here, though, in a sense, we have two Fourier series that are going on. So the first Fourier series is this, right? And so actually, in particular, this is going to be a Fourier sine series where the building blocks for the sine series are these things, and then the coefficients for each of these things are going to be this times this, right? So the coefficients are just not A sub n for the sine series. They're kind of A sub n times cosine of something times t. Likewise, we also have a Fourier sine series here. Right, where the building blocks are these sine terms, and the Fourier coefficients for these sine terms are going to be B sub n times sine of, or times that expression. Okay. So really what we've done, right, is construct two sine series for our solutions. Okay. And we know how to compute Fourier coefficients for sine series. Okay. And so, right, so where do these coefficients come from? Well, those come from matching our general solution to the initial conditions. Okay, and so of course, what do we get? Well, we plug in, here, let me copy this. Move this away for a second. Okay. So those were the building blocks. Over here, paste this. Okay, so for this one, right? So this up here is U of x comma t. So here, plug in t is equal to 0. These terms are going to go to 1. These terms are going to go to 0. So yeah, t equals 0. Okay. So then, all we're left with is a sub n, or the sum of a sub n sine, and that's it. And so that's what we have written here. Okay. Likewise, if we say the derivative at time equals 0 is something, well, first we need to compute the time derivative. So to do that, all right, so du dt at the point x comma t, right, just push the time derivative in. This is going to give us the sum of a sub n sine of n pi over L x. Now the derivative affects this term, so we're going to pick up a c n pi over L, the minus sign. Right, so this is the coefficient coming from differentiating that, times a sine of c n pi over L t, plus, I guess, the sum of, so b sub n. So this is not affected by a time derivative. This is affected by a time derivative. So we're going to pick up a c n pi over L. And then the spatial piece that was unaffected, times cosine n pi over L t with a c in front. Okay. And so now if we want to evaluate this at t equals 0, well, at t equals 0, what do we get? Plug in 0 here. This term is going to go to 0, right? So then this whole thing is also going to go to 0. All the terms in that summation. Cosine is going to go to 1. Okay. So the derivative at time 0, we're just going to get this expression right here. Okay. But this is a Fourier sine series where we have the sine terms. And then these are the coefficients for the sine terms. Okay. And so that's exactly what we have written here. Okay. So the coefficients a sub n and b sub n that are showing up in our general solution, they're either the coefficients or very closely related to coefficients for sine series for these given initial conditions. And again, we know how to compute those. We've been computing them for a while. So what are they? Well, right, for these representations, what are these actual coefficients? Well, a sub n is given by this formula. And then b sub n we can get from this formula. And so we've decided to write it as, right, this is the coefficient for the sine series. So if this is the coefficient for the sine series, the formula tells us that this coefficient is equal to this expression. Of course, you can rearrange it and get what b sub n is equal to 2 over c n pi integral from 0 to L g of x sine of n pi over L x dx. Cool. And so this is a solution, right? So what is the solution to this, to the PDE that we started with, right? This was a PDE that we started with. Well, what is U right here? U is this expression right here, right? These two sine series with these slightly interesting coefficients. Where how do we get these coefficients? Well, these coefficients are given by these formulas. Okay, it's the same technique we've been using since we learned about separation variables. Okay, so right, so the observation is that, right, so the solutions that we've constructed, right, what are the building blocks that go into everything? Well, the building blocks are these pieces, right? So for each n, we get a term like this that shows up in that superposition, where we've chosen to factor out the sine of n pi over L x. Okay, and so these terms right here, these are usually called normal modes for string or whatever other medium is vibrating. These are just the building blocks that we computed. And so then the intensity, kind of the amplitude or strength of each of these normal modes, that's going to be the square root of the coefficients for each of these terms squared. Okay. That's how we're defining the intensity or this amplitude. There are a few ways you can kind of intuit this. One might be that, well, in a sense, what we're working with here, you can kind of think of this as like vector, where you have, one direction is in this kind of cosine function piece. This is one direction you can vary this term. This is the other direction you can vary this term. And so in a sense, this you can think of as vector a sub n and b sub n, where these coefficients are telling you the contribution from kind of this cosine oscillation and the sine oscillation. And so then the norm of this vector, a sub n and b sub n, right? The vector norm is going to be root a sub n squared plus b sub n squared. Okay. So this is one way to kind of intuit. Maybe the more rigorous way is the following. So this thing right here, you can write as, okay, so let me phrase it in this way. So in general, if you have an expression of the form a sub n cosine of omega t plus b sub n sine of omega t, okay, which is almost or pretty much what we have here, where omega is c n pi over l. So if you have an expression of this form, you can rewrite this as the square root of a sub n squared plus b sub n squared times sine of omega t plus theta, where theta is, let's see, arctan of a sub n over b sub n. Okay. So this right here, this is a trig identity. But the nice thing that we get from this trig identity is that, well, right, sine, this is magnitude 1, kind of its absolute value is bounded by 1. So if you look at the magnitude of this expression, right, the maximum the magnitude of this expression can be is when the absolute value of sine is 1, which leaves that this is the magnitude. Okay. So one way to maybe intuit this is, well, if you have this linear combination of sine and cosine, you can rewrite it as just, you know, some amplitude times a sine term. And so then in this case, what we do is we take out that amplitude, and that's going to be, right, the amplitude or the intensity for, you know, this whole piece right here. And so I won't kind of go through how this is derived. We don't really need it for what we're doing. It's not hard, but yeah, okay. Okay, so these are the normal modes. The intensity or amplitude for each of these modes is this expression coming from these coefficients. And so, of course, right, fix a point x somewhere along your string, and then let t increase in time, or kind of let time evolve. Because you're working with these sine and cosine terms, right, the displacement of the string at that point, right, as a function of time, that's going to oscillate between two values because you have these two oscillatory functions here. So the question is, right, well, what is the frequency at which these points oscillate? And so that we're going to call the circular frequency. And that's just a coefficient for kind of time in these cosine and sine expressions. Okay. And so keep in mind, right, this constant c, this showed up in the derivation, the wave equation, where rho naught, this is the mass density of the string. And then T naught, this was the string tension, both of which we usually just assume are constant. Okay. So what are some of the other pieces in play for these solutions that we've constructed? So, right, these solutions, they oscillate in time, right? Fix an x. Time causes a displacement to move up and down in an oscillatory manner. But what we can also do is fix a value of t, right? So fix a value of t here and just see, well, as you vary x, kind of what is the profile? What do we expect will happen, right, to the string? So if you fix a t right here, this is now going to be a constant. And then as you vary x, this is going to oscillate up and down, right? So not only do these normal modes oscillate in time, they also oscillate in space. And so the question is, right, well, kind of what's the rate of oscillation in space? Those we're going to call the natural frequencies of these normal modes. Okay, and these are just very similar to before. These are going to be the coefficients for the variable x in these normal modes. Okay. Okay. And so what we usually like to do with kind of these normal modes, and especially working with these natural frequencies, is we just like to sketch, right, kind of what's happening to these profiles. And so these sketches sort of look like the following. So this is 0, L, maybe this is 1 and -1. So if we just look at sine of n pi over L x with n equals 1, what is that going to look like? So just this right here, this expression is going to look like that, right? Okay. So if we go back here, so that we've sketched this with some fixed t. Okay. And so now what we're going to do is we're going to sketch the same profile of this piece for the natural frequency with n equals 1. But now what we're going to do is vary this expression with t. Okay. And so as we've said, we expect, right, as you increase t, this is going to cause the displacement to oscillate up and down. Okay. So if we increase time a little bit, maybe the displacement of the string will be right there. Increase time a bit more, it'll be kind of right there. Increase time a bit more, it'll be down here. Increase time a bit more, it'll be down here. Okay. Increase time a bit more as well, then it'll go back to here. Increase time, it'll go here, etc. Right, so as you increase t for this normal mode, right, this is a sketch of kind of that mode for various values of t. And so, right, these are kind of this, what we'll call the standing waves for various t, corresponding to natural frequency n equals 1. We can do the same thing for n equals 2. Okay, so sine of n pi over Lx with n equals 2. So in this case, say for one of these fixed values of t, and this is a little off, so let me fix these drawings. -1, 1. So this profile right here is going to be the sketch for the normal mode or the natural frequency with n equals 2. But we can play the same game, right? So as time evolves, the profile will look like that. As time evolves a little more, then it's going to look something like this. As time evolves more, it's going to look something like this. As time evolves more, it's going to look something like that. Time evolves more, then it's going to go back to kind of what we've already traced. That, and then that. Okay. Right, so these are just sketches Sure. But they give us a sense about how these building blocks are behaving, right? So in space, it's the solutions are oscillatory with frequency, natural frequency this. And if we incorporate time, right? Well, in time, the solutions are just going to oscillate as well. And so the profile for these building blocks is going to be contained between kind of this upper bound and this lower bound. But this gives us a quick sense on, right, how these building blocks are behaving. And you can, keep sketching for higher and higher values, right? So for n equals 3, you're going to get kind of 3 of these bumps, etc. Okay, and so right away, what we notice is that, so especially here, there are points that are not displaced for any time. In particular, this point right here at x equals L over 2, for this mode, right, this point doesn't move in time. And so these are what we call nodes or standing points. Right. Yeah. Okay. So it's some vocabulary, some sketches. And so the last thing that we're going to talk about is this interesting phenomenon that solutions to the wave equation have. So in general, right, it turns out that solutions to the wave equation, they behave as kind of a sum of these two wave profiles that just get translated to the left and right. What do we mean by that? Well, suppose that so this is 0 and this is L, and then at some time maybe we have something like this. Okay. So if this is R of x minus CT, let's see. So I'm trying to figure out which direction this is going. 0. Okay. So let's see. So x minus CT, set that to be 0. So then x is going to be CT. So as t increases, the values, so pick this point here, increases, the value that you plug in gets increasing. Okay, here, maybe so I'll write it like this. We're going to have an expression like this. Now, as t increases, as you let time evolve, turns out kind of what happens is, so if this expression actually solves the wave equation, what's going to end up happening is t increases, the profile of the solution is just going to shift to the left or right. And so one way to kind of see that is, right, so this is one of the two terms that showed up in the solution to the wave equation, or for these kind of normal modes. And so if we go back here, right, so distribute the sign to each piece. Okay, so what we're looking at here is now this sine term times the sine term. Okay. So that's what we have here. And so what we can do is we can kind of use some other trig identities to write this thing right here as this linear combination of cosine terms, where the arguments of the cosine terms are x plus or minus CT. Okay. So this whole thing, we're going to write or call R of x minus CT. So this argument is this argument. This whole thing right here, we're going to call S of x plus CT, because we have a plus CT or x plus CT there and there. And so the observation is that, right, well, these building blocks are just going to be these linear combinations of functions that only depend on x plus or minus ct. Okay. And so then as t evolves, right, the behavior of these functions, it's just going to be a shift to the left or right. And so this is a general property of solutions to the wave equation. And some of the homework problems have you kind of writing this out explicitly and then solving some specific problems, highlighting kind of these pieces in the solution.